solid spherical harmonics. And again, there are solutions to the Laplace equation in spherical harmonics. So solid spherical harmonics are the solutions to the Laplace equation in spherical harmonics. Oh, it's good that I emphasize that. And then I say solid because it includes the radial term, like these r's there, so that even though solutions are in a sphere, but the r changes. So the r, you can have it. So basically, it's a solid. It goes within and without. Basically, the r is going to vary. So it's going to be basically if you have a sphere, it's the entire solid in and out. That's what its solutions are for. And regular spherical harmonics are just on the sphere where you basically set r equals to 1, essentially. Now, but these are the general solutions. So anyways, so Laplace equation is just the Laplace operator or Laplacian set to equal 0. So all you do is take this and just set equals 0. So that's the Laplace equation. And you're dealing with harmonics because when it's equal to 0, it's in harmony, and nothing's in and out. It's just always equal to 0. So that is that. So from the Laplacian and spherical coordinates r theta phi, we can write Laplace equation as follows, and that's just basically this. I'm just going to copy our solution. So there's our solution. So we could write it. First, I'm going to write this down using the Laplacian delta f sign. Also equals using this inverted nabla sign, whatever, inverted triangle. It's the same thing as writing that, and this equals to 0. So in other words, we get is this giant formula right here. This right here equals to, or actually I'll make this better. I'll move it down a bit. Yeah, this equals to 0. Yeah, so this whole thing. I'll put it like that. I'll just put it like that. Yeah, so that is what we get. So this whole thing equals to 0. And again, recall the spherical harmonics, just because I'll be uploading this in sections, so might as well just refresh it as well, because this video is pretty giant. So there's the xy axis, this is the z, and then we have an r like this. This is our distance, and this is the theta. And now if this goes down like that, that is going to be our horizontal distance. And this is the angle phi, and this is r theta phi, like that. And this is right angle triangle. And also recall that again from above, x is equal to r cosine phi sine theta. Y is equal to r sine phi sine theta. Z is equal to, Z is just going to equal to, you look at this right here, r cosine theta. And then r is equal to square root, just the distance formula, x squared plus y squared plus z squared. Yeah, so that's what we have there. And again, we have it all the way, when I derived this right here, we already went over this. I'll scroll all the way back up. Yeah, so I already solved these ones for x, y, z, and r. So those are it. And there's the derivations. You could watch that earlier in the video or in the separate video on Laplacian in spherical coordinates, which I'll upload as a separate video after I upload all these, after I finish this video, and so on. Yeah, so that's what we have. Alright, and now that we have basically this Laplacian, the next step is we can apply the separation of variables to obtain, and basically we're going to try to find our function f, and we're going to assume that f can be written as a multiplication of three functions, that e of function of, this is a phi, times it by p is a function of theta, and r, capital R is a function of r. So we're assuming that that the function f could be written like this, and I'm using the terminology in the YouTube channel, the Mike guy on YouTube uses this terminology. I'll just follow that along. All right, so we have that. Now the next step is get our Laplacian in spherical coordinates. So I'm going to copy this. I'm going to go right here, paste. All right, so I'm going to move it like this. This is going to be paste here. All right, so we have this, and now the next step is, well, actually, before I even do that, I'm going to make it smaller. So make it smaller. and then multiply both sides by r. So, or anyways, so now we're going to multiply this by r squared. Yeah, so do that. All right, so if we multiply this out, we're going to get some cancellations here. The r squareds cancel. That's why we're doing that. And this will cancel. We'll just have a left an r there, and this one's going to be an r squared there. So in other words, we're going to get, so this becomes, we're going to get an r squared as the first one, so r squared. And now instead of writing partial derivative, second partial derivative of f in terms of r, well, yeah, this right here, well, we'll just put the f inside. This just is the same thing because these are functions, these are just functions of phi and theta. So that means that if we take the second derivative of f as in terms of r, so second partial derivative, these ones aren't included. So this just equals to, and I'll put our f now. This is going to be, our f is going to be equal to e times p times by r double prime. So this is just this is just a second derivative of r there multiplied by these. These are treated as constants when we're taking partial derivative of f in terms of r. So we just set the other ones as constant. So I'll put this r like that. So that is what that equals to. And now this part here, we're going to get a plus 2. And this is the first partial derivative of f in terms of r. That's just r prime. So this 2r r prime. And actually, don't make a mistake. So it's going to be e times p. Yeah, so e times p times r prime. Because those are, again, we have to include those constants for that partial derivative. Yeah, so they're not actually constants, but they only are when you take the partial derivative. So now, the next setup, this one's gone. So we're going to have a plus a 1 over sine theta. 1 over sine, and also before we go further, so the guy on YouTube, yeah, he does it this way. So first, so we would, instead of using this way, we'll take out write it as the form partial of derivative over partial theta of, and this would just be sine theta partial f over partial theta. And you can see this is the case because this is just chain rule. So take the chain rule. So derivative of sine is going to be cosine theta, then times by partial f over partial theta, and then plus sine times derivative of this right here. It's going to be the second partial derivative of f in terms of theta there. And again, that's just, again, if you go back to the Wikipedia setup here, so this giant thingy, same thing as this, partial over partial theta of sine theta, partial f over partial theta, like that. All right, and so the reason they do this, well, the YouTube channel did this, the Mike guy, it's a bit simpler, so you have less f over there. So now we're going to get now it's going to be sine theta, and then times by this one is the partial derivative of f over partial, it's basically partial derivative of f over partial theta. That's just going to be the derivative here. We're going to write now e, and then EP prime. So we're going to get a times by E P prime times by R. So those are the constants now. The P is a derivative there, as opposed to the R, like that. And yeah, we refer to partial derivative. So this one, move it over. I'll move this over here. So this is going to be, and I'll put a square bracket. We're gonna, because we need to include this part right here. So that's going to be partial over partial theta of this, like that. Yeah, actually, we don't need to do a squared bracket, but we'll just keep it like that. Yeah, I thought we were going to use the second one anyway. So that's what that is. And then the last one is this part right here. That's just going to be plus, put them all in here, and I'll shrink it. Yeah, this one's going to be, let's put a plus like that. This is 1 over sine squared theta. And now this is the second derivative, so everything else constant. This is of the phi, so that just equals to E phi double prime, and then we have PR. And then the whole thing is equal to 0. Like that. Alright, so here's just shrunk it, and we have it all over here. So now the next step is, then this is going to be like this. What I'll do is, I'll put it like this. Next step is going to be, well, we're going to divide every single thing out by P. I'm just going to, instead of putting it there, I'm going to put it like the whole thing. Actually, I'll just do it over here. So now we multiply the whole thing by 1 over 1 over EPR. So we get fractions on each thing, and we cancel out all these extra terms. So that's why we do that. And here I just quickly shrunk everything in here. So we have all that. So then this ends up equaling to, so we're going to get an R squared, and then EP cancels. So then these cancels with this. So again, that's the whole idea, is you just cancel everything out. So we're going to get an EP, E dot P, and then over R. Yeah, this is EP. No, EP is canceled. Yeah, I mean, it's cancels. So we're going to get an R prime, and then over R. So R is not canceled, so we have that over there. So R over R. And then likewise, we're going to get an R, 2R squared, EP, R. So basically all the ones that the R is not there, so EP is gone. So we get an R prime over R. Yeah, this is over R. So in other words, we can combine these. These are EP, those cancel. Put these all together, actually. So this will be a plus 2R, R prime over R. And now the next setup is going to be 1 over sine theta. And then we have, it's 1 over sine theta, and then this one here, these are constants, so it doesn't matter, we could take those out. The EP is our constants, and then those cancel out. They're constants within this partial derivative, so those just cancel out. We're going to get a partial over partial theta of sine theta, and then E's gone, so now we just have a P prime. And then the only thing divided by is going to be this P, like that. Yeah, just divide out the whole thing there. We just put it over everything. Like this, over P. That. Alright, here, just fix that up. And then lastly, we're going to get a plus, this one right here, 1 over sine squared theta. And now this one here, the P's those are gone, so we're just going to get an E double prime over E, like that. Just put it like that. Alright, so that's what we have. We could, divide it out or just leave it like that. So anyways, E double prime, and this whole thing equals to 0. Yeah, because then when we multiply the 0, 1 doesn't change anything, so just 0. Alright, and here I just shrunk it, move it over all into one line here. So now the next step is, well, we can now set the equations equal to their corresponding separation constants. And again, these all equal to 0. So in other words, these are the E functions are in here, there's the P ones in here, and this R ones are in there. So, yeah, these are 3 separated functions, but they all equal 0 at all times. In other words, these are all equal constants. So this one's a constant, etc. This one's a constant, this one's a constant, these are all C1, also C2, etc. So these are all constants. So in other words, we can just set these all equal to their own corresponding separation constants. And to ensure a periodic solution, with the middle function to be set as the difference between the constants, thus ensuring the overall equation sums 0. So basically we just choose this one as a constant, this one as a constant, and this one as the difference. Yeah, and then this one's as the difference between the two. All right, and the constants typically picked like this. So for the first one, we'll look at this part right here. So we'll just look at the, in this one here's, this one typically is written just like these two parts right here. So we'll ignore the sine squared for now. So basically this one is written like this, E double prime of E. And this one is, these are both functions of phi, remember that. So E is a function of phi, going back here. So E is a function of phi, and then this is over function of phi. Yeah, so now this one's equal to negative m squared, and we'll go over that in a bit. And now the next one is this part right here. So this whole setup is, this is going to equal to r squared, r prime, and this is going to be, again, it's function of r. I'll split them all just for completeness. And then plus 2r, and then this is going to be r, r prime. The other one's r double prime, and this is going to be a function of r divided by r. And this, for completeness, is function of r. And now this equals to the function that this one's set up as is equal to n, and then n plus 1. And the reason is so we get the associated Legendre function. Yeah. All right, we'll explain this in a bit. All right. All right, here it's quickly shrunk that in. So if we have these set to these constants, and then this one here is going to be the difference between the two, or just, this one equals to the negative of that. Yeah, so that equals to, let's put this whole thing there. Actually, I'll just copy and paste this whole thing. And just leave it like that. So I'm going to copy this, paste there. Yeah, this one here. And move it here. Yeah, so this one here, this just equals to the negative of those. So it's going to be equal to, so it's a negative, we'll put this negative here, there first. So we'll take the n plus 1. So put a negative n plus 1. And then the next one's going to be, well, minus, but it needs to all equal 0, so we have to include this 1 over sine squared, because this one is the negative m. So basically, it's going to be negative m, but then we're negating that, so it's going to be, well, positive m. Positive m squared over sine squared, like that. Sine squared theta. All right, so we have that. So thus, and again, the reason is so that thus we'll have on this left side here is going to be n plus 1. So this is so they all equal to 0. N plus 1. Now we're going to have the middle term is going to be negative n plus 1, then plus m squared over sine squared theta. So again, this is the middle term, like that. Let's put it like this. I'll just leave it like that. This is the middle one, and then the last one is just going to be this part right here, 1 over sine squared, and be minus, because this one is going to be negative m squared. So that's going to be negative m squared, so negative m squared over sine squared. Yeah, so it equals 0. So again, these cancel, so again, that's the whole idea. That's the whole idea of it. All right, so now we have this, just to go over some notes here. So, and also solving all of this equation. So the first constant, negative m squared, where m is an integer, is selected such that we have a periodic solution. So this one right here. So if we take this and write it down, so if we have e to the phi over e double prime of phi, the second derivative, over phi, e to the phi equals to negative m squared. What happens here now, we could write this as, we'll multiply this over to this side, and then drag it over. What we end up having is move it there, then drag it over. We get an equation like this. We have an e double prime. So we have, again, partial differential. I think this is, I think it's just a differential equation or whatnot. This is gonna be now m squared e phi, phi. This equals to 0. All right, now the way to solve these, and I haven't done too much of this in my actual video series, but I'll probably do that for later in the future. But nonetheless, to solve this, what we'll do is assume, so assume that e of phi, so you can find a solution that's an exponential, equals e to the r phi. So in other words, or actually, instead of using the r, because we already have r for here, I'll just call it a then. E to the a phi. So now if we have the solution is like this, so assume that that is a solution, and we can actually prove that it is, then find a. So we just have to find this this a variable or constant or whatnot. So anyways, all right, so we have this. Well, if we take the derivative of this, derivative e to the e prime of phi, this equals to, well, again, just the derivative of exponential function is just itself. So it's going to be, well, and also, but then you put the a down. That's afterwards. So this is going to be, well, e to the a phi, and then do the chain rule. Derivative of this a phi is going to be a, like that. Yeah, because the derivative of phi would just be 1, and there's just a constant there. So that is that. Now the second derivative is going to be a double prime of phi. We do the same exact thing. So this is a constant, doesn't change anything. Just leave it a, then e a phi, chain rule, put that down, put the a down, so squared. So that's what we have there. So thus what we get now is, now we'll take this entire thing. So e double prime, double prime of phi, that equals to a squared, like that. So a squared e a phi. And then this one here, m squared e of phi equals 0. Plus m squared, and then we'll have a e to the, this is just going to be, this is e a phi equals 0. All right, now the next step is, well, I'm going to divide both sides. So, and the right side 0 doesn't change anything, e a phi. So then, and what ends up happening is these just cancel. So that's all that happens. So we're going to get a squared plus m squared equals 0. Yeah, so in other words, we get A. Yeah, A is going to be, well, it's, yeah, A equals 2. This is going to be moving over to the other side, so we're going to get a negative m squared. And then, yes, be square root negative m squared. Yeah. Actually, before we even write that, I'll just write this down. We're going to get an a squared equals to negative m squared. And the only way to do that is using complex numbers. So in other words, we're going to get an a equals to, and then this equals to plus or minus squared. Because again, you can have minus times minus. It's going to be positive, and plus positive times positive is going to be minus. So this is going to be negative m like this. Yeah, this is going to be m squared. Yeah, so in other words, this equals to, well, I'll keep going, plus or minus negative 1. Yes, negative 1 m. Yeah, this square root, the m squared, just get rid of that. And this is just I. Yeah, this is I equals I. So imaginary number I, which is defined as a square root of negative 1. So in other words, we get A is equal to plus or minus I m. Yeah, so thus we have the solution E of phi, and this is a solution. So E of phi is equal to E, and then this is going to be, this is going to be EA, which is just plus or minus. So A is this right here, EA phi. It's going to be E, plus or minus IM phi. So there it is. So we replaced that's what A equals, and then we just replace this A with IM phi. Yeah, and with plus or minus IM. So that is the solution. That is actually just one solution, but then, now a general solution. General solution is actually a linear combination of the two. Because this is plus or minus, so the general solution is, you can actually, this is a linear combination of this. We're going to get E of phi is equal to, I'll put a C1 as a constant, e to the power of positive IM phi plus C2 e to the power of negative IM phi. So basically you take a linear combination of the two solutions. So that's plus or minus that. And then let me just box this in. So we box this in. So fascinating stuff. All right, so now we have that. Going further, so again, yes, C1 and C2 are constant. So note that the general solution allows for writing every possible solution as a linear combination of two basis functions. And this complex exponential function right here, again, that's complex exponential, are equivalent to trigonometric equations via Euler's formula, as shown in my earlier video when I went over Euler's formula as a matrix. But again, I went over this right here. So Euler's formula, e to the ix, it just equals to cosine x plus I sine x. And then there's Euler's identity, ei pi equals negative 1. That's when you put in pi in here. This one becomes 1. Whoops. This one becomes 1. This one becomes 0. And then that vanishes. So we get ei. That is pretty fascinating. So anyways, so that's the periodicity for our solution. And again, I'm just diving into why they're using negative m squared as the constant, because the video that Mike on YouTube doesn't actually explain why, and then I had to ask Grok AI for that. Anyway, so that's the periodicity for our solution is, and that's basically converting this into the trigonometric equivalent. So basically, we'll take this EIM like that. Yeah, we'll just take the positive side. So we have, this is going to be phi, e to the phi, capital E to the phi equals to exponential e to the power of IM phi. Now this equals to, by Euler's formula, equals cosine x. So it equals cosine. And again, this is ix, so basically m phi. So this equals the cosine of m phi plus, and then this is going to be I sine of m phi. All right, so that's since it's equivalent to the trigonometric setup here. Now we know cosine and sine, they repeat every 2 pi or 360 degrees. So 2 pi radians or 360 degrees. So basically periodic slash repeating, or just repeats. I'll erase this a bit better. And again, it's driving the point why we picked negative m squared. So repeats every And in this case, it's going to be, well, 2 pi. This whole thing needs to be 2 pi. So we'll have to go 2 pi divided by m. And that's because this thing, to get it to equal to 2 pi, we need phi is equal to 2 pi over m. So that this m cancels. So when you multiply by m, this cancels. So that's what phi is. So basically, it repeats every 2 pi over m. And you can go right here. So 2 pi equals to m phi. So in order for 2 pi equals to m phi, we need basically phi. To move over the phi to the other side. So phi is equal to 2 pi over m. So every time this, and then you can put an integer. Basically, it cycles over and over again. So you can multiply this by any number of integers, and so on, and just keeps going, cycling back and forth. So that is that. And you're actually going even further just to drive home the point of this. So the selection of the negative sign in negative m squared allows for our specific complex solution, and the squared ensures we get m to be integer values, and thus our solution is periodic about 2 pi or 360 radians right there. I'm going to change this to 2 pi. And here, just quickly change it to pi. So, or 360 degrees. And again, that's because phi is the azimuthal angle. So remember this phi is the azimuthal angle. So, and then it goes to full 360. We want a periodic, and it basically get the exact same solution. As you repeat, it should have the exact same solution. Actually, I'll draw that as well, just so we drive home the point here. This is going to be our y, z, x. So basically, any solution, if this is the horizontal distance to the point, we want this phi to be the same thing. So if you have phi, then if you go from here all the way around, if we go all the way around like this, I'll do this setup like this. Yeah, this is going to be phi plus 2 pi. So that's 360 degrees. Yeah, phi plus 2 pi. So we want that. Basically we want it equal to the same thing. So in other words, we want e to the phi equals to e to the phi plus 2 pi. So that's what we want. Again, for our spherical harmonics setup. Yeah, so we want those equal. So now if we plug this 2 pi inside our general solution right here, we're going to get a C1. And then e to the, this is going to be negative, this is going to be I m phi plus 2 pi, like that. And then plus C2 e to the negative I m phi plus 2 pi, like that. All right, and if we go further, if we separate this, we get is a setup like this. This is going to be C1 e to the I m phi, same thing as just add them up, and it's going to be e to the 2 pi. Yeah, I m 2 pi. So that's what that is, because you can multiply that inside, just basic power rules. And then C2 is equal to the e negative I m, and then this is negative I m phi, and then times it by e to the negative I m 2 pi. Yeah, so in other words, if this equals to e to the phi, well, we want this right here. I'll put a want equals to 1. So we want this equals to 1. So that's what we want. And then also this one here, we want the e to the negative I m 2 pi equals to 1. Want equals to 1. So that's what we want. So that so then we're just left with the general this equation. So basically we're just left with that if it's equal to 1 there, and it's actually equal there only if m is an integer. So in other words, and also note, this is a Euler's identity, this one right here. So e to the I actually make a note. This is Euler's identity here, but we're going to deal with 2 pi. This is pi, so if we want to just deal with 2 pi, so basically note that e to the 2 pi, e to the I 2 pi, and we just plug this in our equation. This equals to, well, cosine, cosine 2 pi. Yeah, this is Euler's identity that we're doing 2 pi. We're not doing this one. So we're just doing the 2 there. So this is going to be cosine 2 pi. This equals to cosine 2 pi plus I sine 2 pi. All right, and what happens here is, well, we know cosine 2 pi. Just we'll just do a recall. I'll always draw this out. So this is theta, and now if we have a cosine, it's going to look like this. Cosine is going to look like that. That's cosine, and this is going to be cosine. And notice how this is at 2 pi, so it's equals to 1. So this is equals to 1. Yeah, this one equals to 1. Equals to 1. This part right here equals to, well, 0 actually. I'll change this to red, or I'll change the color to red. So this one's going to be like this, and then basically just opposite of that. Yeah, it's going to look like that. So this is sine phi. I'm sine theta. This is just the graph there. I'll go back to black. So in other words, this is 0, and this equals 0. So this whole thing equals to 1. Yeah, so thus e to the I 2 pi equals to 1, and then but we want e to the I m 2 pi equals to 1. And that is true if there's an integer. So you just multiply by 2, it just goes back, it just cycles every 2 pi. So this is just cycles every 2 pi. If you go to another one, go to the 4 pi, so multiply 2 pi by 2. So 2 pi times 1, it's over here. If you times it by 2, you get over here. If you times it by 3, you get 6 pi, and so on. So in other words, it just repeats, and on and on. So in other words, if it's an integer, it just repeats. So thus, e to the I 2 pi n, or I'll put it at m right here, actually, m, equals to 1. If, yeah, or I'll say if m equals integer. Yeah, and this equals, it could be plus or minus, it could be, yeah, negative, I'll put dot, 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 -2, -1, 0, 1, 2, dot, dot, dot. It keeps going on and on. All right, yeah, so I just moved it over here. So thus, we have now, again, now we know why we picked -m squared. So thus, e to the phi equals to e to the phi plus 2 pi. So it repeats every single time. So on our spherical setup here, our spherical domain, every 2 plus pi goes exactly the same thing. So it doesn't matter, yeah, which radians you do. If you could do cycle over and over again. So again, so e to the phi equals e to the phi plus 2 pi, or 360 degrees, or 2 pi radians, if m equals integer. And that is what we wanted. And that's repeated. And again, that's why it was chosen. And I want to dive into that, just so we have some idea of why we're picking this. And then likewise, yeah, and if we scroll back up here, so the equation, this one right here now, so we're going to solve, yeah, so we solve this one here, and again, we defined m, -m squared, so we get that repeating setup there in the solution. Now this one here, this one we actually get the Euler-Cauchy equation, that's what it's called, and then, but then the combination of both, when you throw this in there, what we end up getting is eventually the associated Legendre function in there, which is much more yeah, complicated and beyond the scope of this video, but I'll just put that in there. I won't solve the exact formula directly in this video. Anyways, but so we're going to go over this one right here right now, and then go over why it's n times n plus 1. But ultimately, it's to get that associated Legendre function when you combine them both. So let's examine the second separated function and its chosen constant n times n plus 1, where n is actually a positive integer. And this yields the Euler-Cauchy equation, which we can solve via substitution. All right, so yeah, so let's go back up there again. I'm just going to copy and paste that formula. So this was the constant we chose. N times n plus 1, n is positive integer in this case, so that's pretty interesting. Let's times it by here, but the idea is the same. You're gonna get, you want specific types of solutions on the sphere. All right, so we have this r squared times the double prime r double prime of r plus 2r times r prime, and then divided by r equals n plus n times n plus 1. So what happens now is, well, we can multiply this on this side and then move it over to this side, so we have an equation equaling 0. What we end up getting is a r squared r double prime plus 2r r prime, and then this is going to be multiplied over there, so we subtract a negative, this is going to be negative n times n plus 1 times r equals to 0, like that. All right, now for the solution for this one, we're going to do similar to before. We're going to assume, and it's always that exponential function, which is very useful in mathematics and physics and so on. So let's assume r of r, the solution is going to equal to of the form, or actually, we're not doing the exponential one. It's just a power one, actually. No, forget what I said. Anyways, so r to the power of k. So let's say we have the solution is like that. So if we have that, well, if we take the derivative, r prime, yes, anyways, r prime of r, this is going to equal to, well, the k goes down, then we have r, and then it's going to be k minus 1. And the next one, the second derivative is going to be, I'll just do this here, r double prime of r equals 2, and then put the k down. So we're going to have a k here, and then we have a k minus 1 times by r, k minus 2, like that. All right, so we got that. So now we can combine these all together. So we're going to get an r squared. Yeah, so r squared times it by this whole setup there. That's going to be k minus 1. And then this is going to be an rk minus 2, like that. And then plus, the next one's 2r, and then r prime is going to be k minus 1, like that. And then lastly, we're going to get negative n times n plus 1 times by r, which is just going to be r to the power of k. And this whole thing equals to 0. And now we could start simplifying some stuff. And we could simplify it by, well, these powers right here, this is r to squared. These can combine, so what we end up, and also we can multiply the k inside. So this becomes, I'll just do it like this. This becomes k squared, k times k, and then k times 1, negative k, like that, put a bracket. Now r squared, and then this is r minus 1. That just equals to, yeah, that's the same thing as r. You can add these powers using basic properties of power function. So r squared times r to the power of k minus 1 equals, you combine them all together. So we get an rk. So the 2 minus 2 just vanish. All right, and then plus the next setup here, we have a 2k, and now we have an r to the power of 1. Put those together, we just have an rk, like that. And then we have a minus n plus 1 rk equals to 0, like that. Yeah, so we have rk everywhere, so we just divide everything by that. Divided by r to the power of k, so this cancels, this cancels, this cancels. So we're end up with, we get a k squared. Yes, we get a k squared minus k. So we have a minus k there. I'll just put them all together. Yeah, let's put it all together right here. Minus k. Yeah, then plus 2k minus n plus 1, like that. This equals to just, yeah, it's going, and then it's all equals 0. Just simplify it one more time. This k squared, and add these up together, so we just get a plus k. So 2k minus k is 2k, it's just k. Minus n times n plus 1 equals 0. All right, and now we can apply the quadratic equation here, quadratic equation, and recall this. This is equal to, so if we have, just using basic one, ax squared plus bc, ax squared plus bx plus c equals 0, then the solution is going to be x is equal to, it's going to be, well, negative b. I'll write it from here, then I'll show you the my earlier video on this derivation. So negative b plus or minus square root b minus 4ac divided by 2a. So we have that. Yeah, so that's just a quadratic equation. Let's put a circle like this. So then we put that inside. So we have k in this case. So we have k squared k, and this one is c. So we have k equals to, well, yeah, k, and in this case a is 1. So we have, yeah, basically I'll just put it like this for completeness. So this is going to be a is equal to 1, b is equal to 1, b is equal to 1, and then c is equal to negative n and plus 1. So we just replace it all there. So we have k is equal to, k is equal to, so we have negative b, so negative 1. Yeah, negative 1, I just fixed up that circle. So negative 1 plus or minus. And then, so b is just 1, a is 1. So that's going to be plus or minus. This is going to be, and then we put b as 1, 1 squared is just 1. And then minus 4ac. So what's a is 1. So then we multiply by, it's going to be plus now because we have this n times n plus 1 is c. So we have n and then n plus 1. Like that. All right. And then divide this by 2 times 1. It's just 1. Yeah, let's put it for completeness. Put a 1 like that. Yeah, anyways. So just divide by 2. Yeah, anyway, let's remove it. Anyway, so we got that. This equals, so let's put it for completeness, actually. It's for completeness, just so, because if we put 1 there, and so 1 squared. Put a square there as well. So this equals 2. Yeah, this equals 2 is, fix up the square root sign. So we have a negative 1 plus or minus. And then I'm just going to multiply this inside. So 4 times n, we'll have 4n squared, put it over here, n squared. And then 4 times n times 1, that's just be plus 4n. And then last one, this is 1 squared, just 1, move it over here. And then divided by 2. So that equals that, but also we could note that, let's put this setup here. Note that if we look at this 4n squared plus 4n plus 1, well, we know what that is, because these are just squareds. If we just have a thing called 2n plus 1, if you expand and then squared, what happens if we square this? Well, again, just use your mind here. So this can be 2n times it by itself. So it's going to be 4n squared plus 2n times by this one right here, plus 1. The times 1 is going to be plus 2n. And now you do the same thing on this side when you square it. So this times by this one, then times it by itself. Then times it by itself. So we're going to get a plus 2n, just FOIL it all out. And just move it over here and plus 1. So in other words, this equals to 4n squared plus 4n plus 1. So we could just factor that out. Just complete the square or whatnot. It's pretty straightforward. So I'm just going to leave it like that. So what this means is now we could write k. Let's put the k is equal to negative 1 plus or minus. Now it's going to be, 2n plus 1 squared. Yeah, a squared and square root divided by 2. So then the square root cancels. We're going to be left with a negative 1 plus or minus 2n plus 1 divided by 2. So in other words, what we end up having is, 2 sets of functions equals to like this. This equals to, this equals to negative. So if it's plus, we're going to have to fix that up a bit better. All right, so it can be either negative 1 plus 2n plus 1 and then divided by 2, which equals to, these ones cancel. We're going to get a 2n over 2. That equals to, 2n over 2, it equals n. So we get this one. Or we get negative 1 minus 2n minus 1 over 2. So what we end up having is a negative 1 minus 1 as negative 2, and then minus negative 2n. So in other words, what we get is, and take the negative out, we're going to get a negative. And then this is going to be a divided by 2. So this will be a negative 2 minus 2n divided by 2. So the 1's cancel. So, and then take the 1 out, we just get an n plus 1. All right. Yeah, basically, that's what we get. And I'll just circle these. So that is our solution. We got 2 solutions for k. And I just want to, just for completeness, because I usually do that. So this one here, again, just to show you what it's like that. This becomes negative 2 minus 2n divided by 2. Take it out, take the n's out. We're going to get a, and then cancel this out. We're going to get a, n plus 1. All right. That's all it is. These cancel. We're just going to have a, that's all we got. Anyways, I'll leave it like that. It's pretty straightforward. Yeah, because I didn't want to keep extending this past there. Okay, that's pretty straightforward. So then, thus, general solution, I'll just put it like this. So that is the solution. So right now, so basically that is what e to the k is. Yeah, I mean not e to the k, r to the k. So that's the basis solution, like that. And here I'll just write thus. Yes, I'll just write the basis solution is going to be r of r is equal to r. Yeah, so it's going to be r. Yeah, it's going to be r to the k, which is r to the n, or r to the negative n plus 1. Like that. So that's what it is. Or you could write it in this format. Or actually, instead of that format, I'll just write this as one. Or you could write r of r equals to, like that. So that is our two basis solutions. And then general solution is the linear combination of them to have all possible types by using just a constant setup. So we'll have a general solution using what these are called as basis solutions or something like that. And it's going to be r of r equals 2. And then we're going to put just set up like this. Yeah, just put a constant a and then times it by the first basis solution, r of n, plus constant b, and this is going to be r of n minus 1. Like this. I mean, negative n plus 1. Yeah, let's put it like that. And also, just to match up with our setup, because we had the constants here, if we go back up to the constants we chose it right over here, C1 and C2. So we'll just put C3 and C4 instead. So those are just constants. We'll just put C3 and C4. So C3 Rn plus C4 R negative n plus 1, like that. So that is our solution. And here I just have to write it down. So again, note that the general solution is a linear combination of the two basis functions, these two right there. So a linear combination, just different constants and so on. All right, and also recall my earlier video on the quadratic formula, which we used over here. And also note this square right here. So when you expand that out, notice how we have this multiply this inside there. So this 2n, there's a 4n. There is 2n plus 2n. Anyways, so you recall my earlier video, there's a link to it there, and this is the quadratic formula. I just want to derive it quickly, just for fun. So here we have the ax squared plus bx plus c equals 0, and then completing the square, so if we have x plus d squared, and again we have this at x squared plus 2dx plus d squared. And what you could do here is, the next setup would be, in this case, write it in this form, so divide by a. So we get a x squared over, divide by a on both sides. We're going to get let's do it quickly just for fun here. B over a plus times x plus c over a. Now the next setup is we want to get rid of this x there. So we want to have completing the square setup. We'll have an x plus b over a, 2, divided by 2, because when you multiply it, you'll get this setup. Remember here, there's a 2 there. So divide by 2, so when you multiply it, we get that, and this is going to be squared, and then we also have to, because we're going to get this part squared, so we have to get rid of that, so it won't be any extra set up there, subtracted by this whole thing squared. So this is b squared over 2a squared, and then we still have this one, bac equals 0. Yeah, so that's pretty much what we get. This setup here is just this. And then you solve it, you get this equation. So we have this exactly the same setup here. And then move this over to the other side. We're going to get a negative c over a. And then we get this setup right here, plus b squared over 2a squared. And then to get this, we're going to square root it. And then we subtract by a whole thing by b over 2a. And then simplify, you're going to get this quadratic equation. Anyways. I want to refresh my own memory for that. So let's continue further. And also hopefully you followed that quick derivation. But yeah, we'll watch my video here for more in depth. Anyways, now let's solve the middle term in the Laplace equation, and this term is key to spherical harmonics. All right, and let's scroll back up to that middle equation setup here. So we solved these two here. So we've solved this one. We got this one here. We got this one here, and now the last one in this giant Laplace equation, when we separate the variables, that's this one right here, the one with the p or the sine or the thetas. So this is the one. This is the one we want to find, and this is the one that's key because that's the one with the associated Legendre function. So we set up this setup here. Yeah, so we set up this right here. I'm gonna circle this now. I'm gonna just copy and paste it. It's just easier. Let's copy this and let's move it all the way down here. So let's try solving this and see what we come across. All right, let's paste it and move it here. All right, so we have this, and let's do the same thing. Multiply by p on this side, move it over to this side, and drag it here, and get an equation equaling to 0. So we get and then we get over here 1 over sine theta partial. Then we have a partial over partial theta of sine theta times by p prime. And now this is the multiplied by p there, so minus, this thing is going to be plus now, plus, and yeah, I'll put a giant bracket, so a plus, and we're going to have a n times n plus 1 of a minus m squared over sine squared theta, and then times it by p equals to 0, like that. All right, so now that we have this, and now the next step is, well, we wanted to get this into the associated Legendre formula setup, but again, that's beyond this video, but that's the idea for here. So we're going to go into, I'm going to go let, so I'm going to now let t equals to cosine theta. So if it's equals to cosine theta, now recall the trigonometric identity, so we know that the cosine, or yeah, I'll do it like this actually. Actually, it doesn't matter which way you do it. I'm going to go sine squared theta plus, cosine squared theta plus sine squared theta equals to 1. Recall this identity. So in this case, we're going to replace this with t squared. So we're going to get a, yeah, if that's equals to t squared, yeah, actually, let's do it all in one go. So this equals to, so that equals to t squared. And what I'll do is I'm going to change the sign in terms of t. So we're going to get a, so basically that's t squared. And then move it over to the other side. We're going to get a setup like this. Sine squared. Sine squared theta is equal to 1 minus t squared. In other words, sine theta is equal to plus or minus square root 1 minus t squared. All right, and let's just take the positive value on this one. Yeah, typically that's usually what happens, but I always show the plus or minus just because it's always there. But anyways, everyone just takes a plus sign. So we take a plus, and so what that means now is, well, then, and actually before we go further, well, we gotta solve what this is. This is derivative in terms of theta. And these are, and this one here's partial derivative in terms of theta as well. You could just still write it as d over d theta, just because it's a sine theta, and that's also theta. So what we'll do is, I'm gonna write this. So this derivative right here. So this is gonna be p prime. Let's write p prime equals to, well, dp over d theta, and you could say partial, but again, in this case, the partial is all set up. There's no other variable in this scenario, so you can just write d over dp, it doesn't matter. So this is going to equal to, and again, where theta is a function of t. So in other words, we're using the chain rule, so this equals to dp, dp over dt. So this is the same thing as this one right here. Yeah, because now t is a function of theta, so that then times it by using chain rule, dt over d theta. Yeah, and this equals to, well, dp over d theta, dt, times a dt over d theta. That's just going to be, well, derivative of cosine theta is going to be negative sine theta. Negative sine theta there. All right, so what this equals to now, well, if we look over here, this is a 1 over sine, and then we have a partial over partial theta, or d over d theta of this function there. So in other words, we could rearrange this so that we have move this sign over to the other side. We're going to get a 1 over negative sine. I'll just put a 1 over negative sine theta, and then this is going to be over to this side here. Yeah, this is going to be, let's move it like this. This over to there. This is going to be dp over d theta. This equals to dp over dt. like that. So I will box this because now we could replace this whole thing here. This gets replaced now. Or better yet, this part. Yeah, this part gets replaced. Alright, so yeah, let's just start changing everything up. So this is gonna go, I'm gonna make this zoom out a bit so that I could put this arrow like that. Yeah, so right here. Alright, so we're back in. Yeah, alright, here I just fixed that up so that arrow just, thus, we're gonna get now, this becomes, yeah, 1 minus, and also there's a, note there's a negative there too. So this becomes negative dp over dt, or it's going to be the function inside, so d over dt of this inside. That's going to be, well, sine squared. We know sine squared is equal to just the positive of here, square root 1 minus t squared. So we're going to do a square root 1 minus t squared, and then times it by, we'll make this a square bracket. And that's because the next one here is p prime. And, well, we know p prime is just going to be equal to this dp over d theta. That equals to dp times it by negative sine theta, where sine theta is equal to this one. So it equals to -1. This equals to the negative of sine theta, which is 1 minus t squared. So this becomes over there. And, yes, put that like that. I'll just put it like that. And then we have this dp over d theta. dp over dt. Box it in. And then the next setup is just add the remaining terms here. Yeah, I'll just copy this setup here. Actually, no, yeah, I don't need to copy. I'm just going to put like here, plus now. Plus a square bracket. This is going to be n times n plus 1. And then minus, and then it's going to be an m squared divided by sine squared and times all times by p. M squared divided by sine squared is equal to 1 minus t squared. So 1 minus t squared times by p. And this whole thing equals to 0. Alright, here I quickly just shrunk everything in, fixed it all up. But yeah, so we have this now. And now these two combine. Well, this is just, and also there's a negative right here. So you can move the negative inside and basically just get rid of all this. This one becomes positive now. Yeah, that becomes positive. Yeah, so that becomes positive. And also here now we have a square root t minus 1 minus t squared times square 1 minus t squared. Well, the square roots add up, so 1/2 plus 1/2 adds up. So this is equals to 1 minus t squared. So what that means is, well, we can take this now derivative using a chain rule. And this, using chain rule, what we'll get is, so we're gonna get right here, we'll put it like this, so yeah. Yeah, put this, yeah, like this whole thingy. Yeah, let's put a better arrow like this. So we're gonna get a 1 minus, well, first of all, you know, this 1 minus t squared. And then take the derivative of this one here, dp over dt, so we're gonna get a second derivative. In other words, we're gonna get a p double prime. And it's, yeah, we don't need the partial one because it's all just in terms of t there, like that. And then plus, now we have to take the derivative of this one here. This is going to be, well, negative. This is a derivative of 1 is going to be 0. Derivative negative t squared is going to be, put the 2 down, minus 1. So we're going to get a minus 2t, and then just regular p prime. And then plus, this setup, this whole thingy is just going to be a n times n plus 1 right here. Yeah, fix that up, n plus 1 minus m squared over 1 minus t squared times by p equals to 0. And here, just move the arrows around. I'm going to box this whole thing. And this is all we need to get to. And I'm not going to basically solve this directly because this is something that's actually been studied a lot. This is the associated Legendre function. All right, and yeah, so this is pretty much what we need to get to. And now we're gonna just plug in the solution from Wikipedia and so on. So this is the associated Legendre equation. Notice exactly the same setup here, and I'll probably do videos in the future deriving this the exact solution. yeah, in a separate video. But anyways, yeah, otherwise it'll be way too outside the scope of this video. So this is the associated Legendre equation, and notice this is exactly the same thing, but we'll replace x with t in our case here. And this is a this is a second derivative of d squared over dx squared. That's the second derivative, that's just p prime. And they write this PLM setup there. Notice the PLM, and that's because there's this setup L, and there's M here, and there's an N here. But now we're using N. So in our case, we use N, and we use T instead of L and X. But we solve the M there. Notice here, and then there's minus 2x. Yeah, that's the 2t. Now there's the this is the derivative over here, dx over dt. That's just p prime. That's p prime. There's the, and then there's PLM. That's just the solution to it. Anyways, that's p, and there's n times n plus 1 is L times L plus times L plus 1. Then there's minus m squared over 1 minus t squared, and then this is m squared divided by 1 minus x squared, and there's PLM or p, and a equals 0. And then you could also write it or this format, d over dx, and this setup here. And this is exactly the same setup we had. We just expanded it out. That's this part right here, d over dt of 1 minus t squared times it by dp over dt. And this one is d over dx of 1 minus x squared times by the derivative of this p there. Yeah, exactly the same thing. So where L and M are integers and refer to the degree and order, not a power, of the associated Legendre polynomial. So it's not a power, it refers to some other degree and order, respectively. So the degree, so the degree is L, and then the power is M. And also, but it's not an actual power, order, the order is M. And this is for the equation, and this is where those whole idea of magnetic quantum numbers arise as well, because basically you plug in these into this giant solution, which I'll get to, and those give you your respective solutions. Anyways, the above equation has non-zero solutions that are non-singular or regular, and means p remains finite, bounded, continuous, and differentiable, so it doesn't blow up to infinity and other stuff like that, on negative 1 to 1 only if n and m are integers. With this one, I wrote n here. I'm just going to replace it here. I meant m. Initially, I wrote it with just converting everything to the one I'm using. So I'm using n here just because the mic guy on YouTube used n. But anyways, for the Wikipedia, they typically all use L, but again, it's hard to write like that. Anyways, and m are integers with so where m is less than or equal to L, and m is greater than or equal to 0, or trivially equivalent negative values, replacing m with negative m. So it'd be the same thing, and but you could replace it with negative m. The solution is given in terms of the Legendre polynomials PL of x. So this is the associated Legendre function or equation, and the solution is given in terms of the normal Legendre polynomials. This is what I mean. It's beyond the scope of this one, of this video. So m is greater than or equal to 0. And again, I haven't covered this before either, so this will be new to me. But anyways, so PLM of x equals to negative 1 to the power of m. And so this is the solution of it. And then this is going to be times by 1 minus x squared to the power of m divided by 2 times by the mth derivative in terms of x of PL of x, where PL of x is the Legendre polynomials. All right, note the factor negative 1 to the power of m is known as the Condon shortly phase, but some authors omit this phase factor, which just rotates and shifts the phase or angle, etc. Just multiply by negative 1 and so on. And so when this becomes negative, when m becomes like even number, this will be positive. When it's odd number, it will become negative. Anyways, and those are integers again. Remember, they're integers where are integers. So L and M are integers. So and also where PL of x is the Legendre polynomials is the solution of the Legendre equation. So this is the associated Legendre equation, and this is the normal Legendre equation: 1 minus x squared times second derivative of PL of x minus 2x, and then this is times it by derivative of this PL of x. plus L times L plus 1 times of PL of x equals 0. And then by Rodrigues formula, so we can obtain PL of x. And again, this is what I mean by all we had to do was get up to here. And then there's a bunch of research done on this specific form here. And again, that's why these constants were picked as well. So we get the solutions in those other ones, and we have then the difference. We get this. We get the associated Legendre equation. All right. So then by Rodrigues formula, we can obtain PL of x. We can obtain PL of x as this is going to be as, and then PL of x equals to 1 divided by 2 to the power of L times L factorial. So there's a factorial showing up somehow. And then times it by dl over dxl. This is the Lth derivative of x squared minus 1 to the power of L. All right, so this looks like some Taylor series type stuff, it appears, I think. Anyways, I'll see what happens when I derive it in a future video. So then PLM can be expressed as, if you just throw this inside. So if you throw this PL inside this solution here, so that's this one here, throw it inside. So now the mth derivative of this right here. So then the PLM of x can be expressed as PLM of x equals to negative 1 to the power of m divided by 2L times L factorial, divided by 2 factorial. So we have, this is the PLM of x, so we have this one here, and then we have to include these two terms, and then we multiplied by 1 minus x squared power of m divided by 2. That's from the associated part right here. And then we have, now it's the PL of x. Now we take the mth derivative, and even though we already took over here, this one here, the Lth derivative of this. So we're going to have to take the combined derivative, the L plus mth derivative of x squared minus 1 to the power of L. Yeah, so I told you all this is, I don't know if you guys are ready for this. Anyways, the derivation of the Legendre polynomials are outside the scope of this video, but I may cover them in a future video. See Mike the Mathematician's playlist for now. So there's a playlist there on solving these. I'll click this to see what happens. So if you click the playlist, it has a bunch. He kind of like fast forward derivation, so you might get lost. And then, but hence why I'm doing these videos in a slow motion fashion. All right, so it's loading up. There it is. It says spherical harmonics, associated Legendre equation, and so on. Legendre polynomials. Okay, epic stuff there. I'll close this. So now, plugging all of this together, we obtain our solution for the solid spherical harmonics, and again, in terms of the associated Legendre polynomial. So in terms of this giant thingy, but we'll use n instead of L. Yeah. So what we're gonna get is, well, let's just find our starting point. So I'm going to put first of all, and we're going to get solid spherical harmonics. Yeah, plugging all together in the solid one, again, includes the radial term and so on. So let's just go back to put it all together. So I'm going to write now our starting point where we started off with the Laplace equation. But instead of using the one I wrote, I'm just going to take the one we solved earlier and then show it on Wikipedia. So we go back up here. So f is equal to a function of these right there. The separated variable. So we have this right here. We can copy that, or I'll just copy this one here because this is what we solved in the earlier in this video. That's this part right here. So I'm going to write that. It's just more compact. And then we go back into here and start putting it all together and erase this. All right. Okay, paste it, and we have this. Okay. So thus we have f. F is a function of, let's put it all together, equals to, in separated variables, e of function of phi times it by p. Or actually, instead of even that, I'm going to erase it. I'm going to say f is a function of, I'll put this as r theta phi, and this equals to now, this equals to our setup, equals to separated variables, is separated function, e as a function of phi, times it by, and I'll write the r one first, in the middle there, r of r, and then times it by p of theta. The reason put that at the end because that's the associated set of their PLM. So now this equals to, so we're gonna get now this equals to, I'll put it like this. Yeah, this equals to, well, the first one is gonna be, well, we know that one was just C1 e to the im phi plus C2 e to the negative im phi, like that. And that's we can go over there. That's the one we solved earlier. Let's go back all the way there just to show you. Again, it's like, how do you get all this in there? So this was the one I derived here. So C1 e to the im phi plus C2 e to the negative im phi. And then the second one is going to be this one here. That's the, this one's going to be C3 Rn and then C4 Rn, r to the minus n plus 1. All right, so that's going to be, again, that's why we put those in order like this. Then times it by C3 r to the n plus C4 r to the negative n plus 1, like that. And then lastly, times it by P of, this is going to be, now this is the Legendre. So instead of Lm, we have Nm. All right, instead of x, we have t. So we go back up here. So we have t, and remember what t is equal to. T is equal to cosine theta. So we just plug in cosine theta in there. So we're going to replace everything with what we have, times it by p n m. So instead of L, we have n. So instead of L, we have, we have m there at the top there. So where's the equivalent there? Yeah, so we have n, m. And then cosine n, instead of x, instead of t, we have cosine theta. All right. And here I move this over to this side. What I'm going to do is I'm going to box this whole thing out because this is our solution. This is our solution. And for completeness, let's put in our p and m, our associated Legendre function. So where we'll go t is equal to cosine theta. This t is equal to cosine theta. And right here, so and we have, so we have, this is going to be our p n of m. I'm going to put a t now instead of cosine theta. So that equals 2. And then we put this set up here. So this is going to be negative 1 to the power of m. And then times by 1 minus x squared power of m minus 2, divided by 2. But that's going to be a t. And it's dm over dxm and then pl of x. So that's going to be now negative 1 to power of m times it by, I think there's, 1 minus, this is going to be right here, 1 minus t squared power of m squared. So 1 minus t squared power of m divided by 2, and then times it by dm over dtm, the mth derivative of Pn of t, the regular Legendre polynomial. And we could see this again. Just double check quickly. This is the PL, negative 1 power of m, and then 1 minus t squared to power of m divided by 2, and then this one dm over dtm, like that. So there's dtm is 1 minus t squared. Pn of t, and then now lastly, or keep going, and Pn of t, the regular Legendre polynomials, this equals to, let's scroll up to it, that's this part right here, so 1 divided by 2n divided by n factorial, so 1 divided by 2 to the n factorial, and then the next setup is going to be, well, this can be the nth, or the L or nth derivative of t squared minus 1 power of n, so this is going to be the nth derivative of t squared minus 1 power of n. So that's what it is, I think. It's double, there it is, minus 1 power of n. And that's fascinating stuff. And so now we put it all together, or we can go write down the whole thing, and then Pn of t, or actually we could probably just put it all into here. So Pn of m of t is equal to this part right here, negative 1 power of m, and then combine it with this part here. So we're going to get a 2 to the power of n factorial. Now we have this part right here, 1 minus t squared m divided by 2. And now we combine these derivatives of this thingy. That's going to be the nth plus mth derivative in terms of t of t squared minus 1 power of n. Unbelievable. All right, here's shifted it. I'm going to bold this in. All right, and if we go back up, just double check. That's this formula. So we have PL of x is one. This is one negative 1 power of m, and then this can be 2L L factorial, or in other words, n 2n n factorial. That lines up, and then 1 minus t squared power of m divided by 2, and then there's the L n plus m, and then this is going to be t squared minus 1 power of n. Yes, absolutely fascinating stuff.